Q1. What are endogenetic processes in the lithosphere? Definition: endogenetic processes are internal Earth movements that originate from the energy within the Earth's interior. They are responsible for shaping and modifying the Earth's crust. Facts: they are driven by geothermal and radioactive heat. They occur beneath the Earth's crust. They include diastrophic, slow, and sudden, fast, processes. Body. Explanation: the heat inside the Earth sets mantle convection currents in motion. These currents push, pull, or collide tectonic plates, leading to folding, faulting, earthquakes, and volcanism. These processes continuously build and destroy landforms. Examples: folding, Himalayas due to Indo-Eurasian plate collision. Faulting, San Andreas Fault, USA. Volcanism, Mount Fuji, Japan. Earthquakes, 2011 Japan earthquake and tsunami. Impact: positive, creates fertile volcanic soils, Java, Indonesia. Builds natural resources like coal, petroleum, and minerals. Provides scenic landscapes and tourist attractions. Negative, earthquakes destroy life and property. Volcanic eruptions cause loss of biodiversity. Tsunamis devastate coastal communities. Causes mantle convection currents. Radioactive decay in the Earth's core. Plate tectonic interactions, collision, subduction, divergence. Control: preparedness, earthquake drills, disaster awareness programs. Technology: seismic monitoring, volcanic prediction, tsunami warning systems. Infrastructure: earthquake-resistant buildings, hazard mapping in risk zones. Conclusion: endogenetic processes are essential in shaping the Earth's dynamic surface. Though destructive at times, their long-term role in mountain building, mineral formation, and soil fertility makes them crucial for human civilization. Q2. Differentiate between diastrophic and sudden endogenetic processes. Definition: endogenetic processes are divided into diastrophic, slow, long-term, and sudden, abrupt, short-term, processes. Facts: diastrophic, act gradually over millions of years. Sudden, release enormous energy in seconds or minutes. Body. Explanation: diastrophic processes involve deformation of Earth's crust through folding, faulting, uplift, and subsidence. Sudden processes include earthquakes, volcanic eruptions, and landslides, which occur unexpectedly with severe impacts. Examples: diastrophic, formation of Himalayas, folding. Great Rift Valley, Africa, faulting. Sudden, 2015 Nepal earthquake. 1883 Krakatoa volcanic eruption. Impact: diastrophic, provides new landforms, mountains, valleys. Helps in groundwater storage and mineral availability. Sudden, causes destruction of cities and villages. Triggers tsunamis, loss of human life, and displacement. Causes: diastrophic, continuous plate movement, mantle convection currents. Sudden, slippage of tectonic plates, pressure release, magma accumulation. Control: diastrophic, land use planning. Slope stabilization in mountainous regions. Sudden, seismic zoning and earthquake-resistant structures. Early warning systems for volcanic eruptions and tsunamis. Disaster response training. Conclusion: diastrophic processes shape the Earth slowly and constructively, while sudden processes are abrupt and destructive. Together, they highlight the Earth's internal dynamism and the need for human preparedness. Q3. Explain the role of volcanism as an endogenetic process. Definition: volcanism refers to all processes through which molten rock, magma, gases, and other materials are expelled from the Earth's interior to its surface. Facts: volcanism is a sudden endogenetic process. It occurs mainly along plate boundaries, subduction, divergent zones. It forms important landforms such as volcanic cones, lava plateaus, and calderas. Body. Explanation: when pressure builds in the Earth's mantle, magma rises through cracks and vents in the crust. Upon reaching the surface, it erupts as lava, ash, and gases. Over time, repeated eruptions build volcanic landforms. Volcanism plays a crucial role in recycling Earth's crust and releasing gases essential for atmosphere formation. Examples: Mount Vesuvius, Italy, destroyed Pompeii in 79 CE. Mount Fuji, Japan, stratovolcano near Tokyo. Deccan Traps, India, lava plateau formed 65 million years ago. Impact positive, fertile volcanic soils, Andes, Java. Source of geothermal energy, Iceland. Creation of tourist attractions and minerals. Negative, destruction of settlements, Pompeii, Italy. Ash clouds disrupt aviation, Eyjafjallajökull, 2010. Climate impacts due to ash blocking sunlight. Causes: subduction zones, oceanic plate sinking beneath continental plate. Divergent boundaries, mid-ocean ridges. Hotspots, Hawaii Islands. Control prediction, monitoring volcanic tremors, gas emissions. Preparedness, evacuation drills, hazard mapping. Mitigation, exclusion zones around active volcanoes. Conclusion: volcanism, though destructive, is vital for Earth's renewal. It shapes landscapes, enriches soils, and supports ecosystems, making it both a hazard and a resource for humans. Q4. Describe the types of volcanoes with examples. Definition: volcanoes are openings in the Earth's crust through which magma, gases, and pyroclastic materials erupt. They are classified based on shape, eruption style, and material. Facts: major types: shield, composite, cinder cone, and caldera. Distribution: mainly along the Ring of Fire, Pacific Ocean. Body. Explanation: 1. Shield volcanoes formed by fluid basaltic lava flows. Large, broad, dome-like structures. Example: Mauna Loa, Hawaii. 2. Composite volcanoes, stratovolcanoes, formed by alternate layers of lava and ash. Steep-sided, highly explosive. Example: Mount Fuji, Japan, Mount Vesuvius, Italy. 3. Cinder cone volcanoes, small, steep-sided cones made of pyroclastic fragments. Short-lived eruptions. Example: Paracutin, Mexico. 4. Caldera formed when a volcano collapses after a massive eruption. Often filled with water to form lakes. Example: Crater Lake, USA. Examples: Summary table, type example location shield Mauna Loa Hawaii, USA composite Mount Fuji Japan cinder cone Paracutin Mexico caldera Crater Lake Oregon, USA impact positive, volcanic soils agriculture, Java, Indonesia. Formation of new islands, Surtsey, Iceland. Source of minerals, sulfur, pumice. Negative, hazard to human life and property. Air pollution, climate change. Lava flows and pyroclastic flows destroy ecosystems. Causes: plate tectonic movements, subduction/divergence. Accumulation of pressure in magma chambers. Hotspot activity. Control: seismic monitoring of volcanic tremors. Satellite imaging of thermal changes. Hazard mapping and restricted settlement near active zones. Conclusion: different types of volcanoes reflect Earth's internal dynamism. While they bring hazards, they also enrich the environment, highlighting the dual role of nature in creation and destruction. Q5. What are earthquakes? Explain their causes. Definition: an earthquake is the sudden shaking or vibration of the Earth's surface caused by the release of stored energy in the Earth's crust. Facts measured using the Richter scale and seismographs. Focus: point inside Earth where energy is released. Epicenter: point on surface directly above the focus. Body. Explanation: earthquakes occur when stress builds up in rocks along fault lines or plate boundaries. When this stress exceeds the strength of rocks, they rupture, releasing energy as seismic waves. Examples: 2001 Bhujay earthquake, India. 2015 Nepal earthquake. 2011 Tohoku earthquake, Japan. Impact positive, exposure of minerals and groundwater. Negative, collapse of buildings, tsunamis, loss of life, economic damage. Causes plate tectonic movements, collision, divergence, transform. Volcanic activity. Human-induced activities, reservoir-induced, mining, nuclear testing. Control earthquake-resistant building design. Seismic hazard zoning. Early warning systems and public drills. Conclusion: earthquakes are destructive but natural phenomena of Earth's dynamics. Preparedness and scientific planning reduce their adverse impacts. Q6. What are the types of earthquakes? Definition: earthquakes are classified based on their causes, depth of focus, and region of occurrence. Facts: classified mainly into tectonic, volcanic, collapse, and explosion types. Depth: shallow, intermediate, and deep focus earthquakes. Body: explanation. 1. Tectonic earthquakes caused by movement of lithospheric plates. Most common type. Example: San Andreas Fault, USA. 2. Volcanic earthquakes triggered by volcanic eruptions. Example: Krakatoa eruption, 1883. 3. Collapse earthquakes caused by collapse of underground caves or mines. Example: earthquakes in mining regions. 4. Explosion earthquakes man-made, caused by nuclear tests or explosions. Example: nuclear test quakes in Nevada, USA. 5. By depth of focus: shallow focus, 0.70 km most destructive. Intermediate focus, 7,300 km. Deep focus, 300-700 km. Examples: summary table, type cause. Example: tectonic volcanic collapse, explosion, plate movement. 2015 Nepal earthquake, volcanic eruption, Krakatoa 1883, mine/cave collapse, mining regions in USA, human nuclear activity, Nevada nuclear tests. Impact: shallow quakes cause maximum destruction. Volcanic quakes are usually localized. Explosion and collapse quakes are limited in scale. Causes: natural tectonic and volcanic activities. Human activities like mining and nuclear tests. Control: monitoring seismic activity. Land use regulation in earthquake-prone zones. Strong infrastructure design. Conclusion: earthquakes differ in type and scale but all demonstrate the Earth's internal dynamism. Classification helps in understanding and preparing for their impacts. Q7. What are fold mountains? Explain with examples. Definition: fold mountains are mountains formed by the bending and folding of Earth's crustal rocks due to compressional forces caused by plate movements. Facts: they are the youngest and highest mountains. Formed mainly at convergent plate boundaries. Contain rich mineral resources and forests. Body. Explanation: when two tectonic plates collide, the sediments deposited in geosynclines are compressed and folded. These folds rise upward, forming mountain ranges. The intensity of folding depends on pressure and rock type. Examples: Himalayas, India, Nepal. Alps, Europe. Andes, South America. Impact: positive, source of rivers, biodiversity, minerals, tourism. Negative, earthquakes, landslides, transport difficulties. Causes: plate convergence and compression. Movement of sediments in geosynclines. Control: afforestation and slope stabilization. Earthquake-resistant structures. Proper planning of settlements and transport routes. Conclusion: fold mountains are dynamic features of Earth, providing resources and ecosystems but also posing challenges. They symbolize the power of endogenetic forces. Q8. What are fault block mountains? Explain with examples. Definition: fault block mountains are mountains formed when large crustal blocks are uplifted or tilted along faults due to tensional or compressional forces. Facts: formed by vertical displacement along faults. Characterized by steep sides and flat tops. Often associated with rift valleys. Body, explanation, when tensional forces pull the Earth's crust apart, blocks of rocks are displaced. The uplifted blocks form block mountains, horsts, and the lowered blocks form rift valleys, grabens. Examples: block mountains, Black Forest, Germany, Sierra Nevada, USA. Rift valleys, East African Rift Valley, Narmada Valley, India. Impact positive, provide fertile valleys, groundwater storage and minerals. Negative, prone to earthquakes, limited agriculture on slopes. Causes tensional forces creating normal faults. Compressional forces creating reverse faults. Control avoiding settlement in seismically active valleys. Land use planning in fault zones. Scientific monitoring of crustal movements. Conclusion: fault block mountains highlight the role of faulting in shaping the Earth's crust. They are both resource-rich and hazard-prone, requiring careful management. Q9. Describe the volcanic landforms formed on the Earth's surface. Definition: volcanic landforms are relief features formed due to the eruption of magma, lava, ash, and gases from volcanoes on the Earth's surface. Facts classified into extrusive, surface, and intrusive, below surface, landforms. Built by volcanic eruptions, lava flows, and deposition of pyroclastic materials. Body, explanation, when magma reaches the Earth's surface, it cools and solidifies to form different landforms. These depend on the type of eruption, viscosity of lava, and tectonic setting. Examples of extrusive landforms: 1. Shield volcano, broad, gentle slopes, basaltic lava. Example: Mauna Loa, Hawaii. 2. Composite volcano, stratovolcano, steep slopes, alternate layers of lava and ash. Example: Mount Fuji, Japan. 3. Cinder cone, small, steep cones of ash and cinders. Example: Paracutan, Mexico. 4. Lava plateau, extensive flat upland formed by repeated lava flows. Example: Deccan Traps, India. 5. Caldera, large depression formed after collapse of a volcanic cone. Example: Crater Lake, USA. Impact positive, fertile soils, geothermal energy, minerals, tourism. Negative, hazardous eruptions, lava flows, destruction of settlements. Causes: magma rising due to tectonic forces. Plate convergence, divergence, and hotspots. Control monitoring gas emissions and seismic activity. Establishing exclusion zones near active volcanoes. Hazard maps and evacuation drills. Conclusion: volcanic landforms reveal the constructive and destructive role of volcanism. They enrich landscapes and resources but also demand disaster preparedness. Q10. Describe the intrusive landforms formed by volcanism. Definition: intrusive landforms are igneous rock features formed when magma cools and solidifies inside the Earth's crust. Facts: also called plutonic landforms. Exposed later due to erosion of overlying rocks. Body, explanation, magma that does not reach the Earth's surface cools slowly beneath the crust. This leads to the formation of coarse-grained intrusive rocks and distinct landforms. Types of intrusive landforms: 1. Batholiths, large, dome-shaped intrusive bodies, form mountain cores. Example: Sierra Nevada, USA. 2. Laccoliths, mushroom-shaped bodies that push overlying strata upwards. Example: Karnataka, India. 3. Sills, horizontal sheets of igneous rock intruded between layers. Example: Hwyn Sill, UK. 4. Dikes, vertical wall-like intrusions cutting across strata. Example: Deccan Trap Dikes, India. 5. Faccoliths, lens-shaped intrusions formed in folds of rocks. Examples: batholiths in the Himalayas. Dikes in the Deccan Plateau. Impact: provide minerals like granite, copper, gold. Affect groundwater storage. Lead to uneven terrain when exposed. Causes: magma intrusion due to high pressure and tectonic movements. Control geological surveys for safe construction. Proper mining practices in intrusive rock regions. Conclusion: intrusive volcanic landforms highlight the slow but powerful role of magma within the crust. They are crucial for resources and provide insights into Earth's internal processes. Here are the next two Q&As, Q11 and Q12, in the same structured format. Q11. What are the different types of earthquake waves? Definition: earthquake waves are vibrations generated during an earthquake that travel through the Earth's body and surface. Facts classified into body waves and surface waves. They provide important information about Earth's interior. Body. Explanation. 1. Body waves travel through the Earth's interior. 2 types, P waves, primary/longitudinal travel fastest, arrive first. Move through solids, liquids, and gases. Cause push-pull motion. S waves, secondary/transverse slower than P waves. Travel only through solids. Cause up-down and sideways motion. 2 surface waves travel along the Earth's surface. Cause maximum destruction. 2 types, love waves, horizontal shearing motion. Rayleigh waves, rolling motion like ocean waves. Examples: 2001 Jaya earthquake showed destructive surface waves. Seismographs record P and S wave arrival times. Impact P waves used in early warning systems. Surface waves cause collapse of buildings and infrastructure. Causes sudden release of energy in Earth's crust. Control seismograph monitoring for wave patterns. Designing structures to withstand surface wave damage. Conclusion: earthquake waves reveal the structure of Earth's interior while also being responsible for the destruction during earthquakes. Q12. How are earthquakes measured? Definition: earthquakes are measured using scales and instruments that determine their magnitude, energy released, and intensity, impact on surface and humans. Facts recorded by a seismograph. Magnitude, objective measurement. Intensity, subjective, impact-based. Body. Explanation. 1. Seismograph instrument that records seismic waves. Provides data on arrival of P, S, and surface waves. 2 scales of measurement. Richter scale, measures magnitude, energy released. Logarithmic scale from 0-9. Moment magnitude scale, MW, modern and more accurate than Richter. Used for large quakes globally. Modified Mercalli intensity scale, MMI, measures intensity based on human perception and damage. Scale from I, least, to 12, most destructive. Examples: 2001 Jaya earthquake, 7.7 MW. 2015 Nepal earthquake, 7.9 on Mercalli scale. Impact magnitude helps compare earthquakes scientifically. Intensity helps governments assess relief measures. Causes: plate tectonic stress release causes the need for measuring tools. Control seismological monitoring networks. Real-time data sharing for early warnings. Conclusion: measuring earthquakes through magnitude and intensity scales is essential for scientific understanding, disaster preparedness, and effective response. Shall I go ahead with Q13, distribution of volcanoes, and Q14, Pacific Ring of Fire, next? Here are the next two Q&As, Q13 and Q14, in the same structured format. Q13. Explain the global distribution of volcanoes. Definition: volcanoes are unevenly distributed on Earth, occurring mainly along tectonic plate boundaries and hotspots. Facts: about 80% of volcanoes are found along convergent plate boundaries. Major zones: Pacific Ring of Fire, Mid-Atlantic Ridge, African Rift Valley. Body. Explanation: volcanoes are concentrated in specific belts where tectonic activity is highest. 1 Circum-Pacific Belt, Ring of Fire around the Pacific Ocean. Highly explosive volcanoes. Example: Mount Fuji, Japan, Mount St. Helens, USA. 2 Midworld Belt, Mediterranean Himalayan Belt from Mediterranean Sea through Himalayas to Indonesia. Example: Mount Etna, Italy, Krakatoa, Indonesia. 3 Mid-Atlantic Belt, along mid-ocean ridges. Example: Icelandic volcanoes. 4 intraplate hotspots, away from plate boundaries. Example, Hawaii Islands, Yellowstone, USA. Examples: Mauna Loa, Hawaii, Mount Etna, Italy, Mount Fuji, Japan. Impact creates new land and islands. Fertile soils and minerals. Causes disasters, tsunamis, and climate changes. Causes subduction zones, divergent ridges, hotspots. Control monitoring volcanic belts. Hazard mapping of active zones. Conclusion: volcanoes are concentrated along belts where tectonic activity is high. Their global distribution reflects Earth's dynamic internal processes. Q14. What is the Pacific Ring of Fire? Explain its significance. Definition: the Pacific Ring of Fire is a horseshoe-shaped belt of intense volcanic and seismic activity surrounding the Pacific Ocean. Facts: contains 75% of world's active volcanoes. About 90% of earthquakes occur here. Extends 40,000 kilometers. Body. Explanation: the Ring of Fire is formed due to subduction of oceanic plates beneath continental plates. This results in frequent volcanic eruptions, earthquakes, and tsunamis. It stretches from South America to North America, across Japan, Philippines, and down to New Zealand. Examples: Mount Fuji, Japan. Mount St. Helens, USA. Krakatoa, Indonesia. Chilean Andes volcanoes. Impact: positive, fertile soils, geothermal energy, new land formation. Negative, frequent earthquakes, volcanic eruptions, tsunamis, e.g., 2004 Indian Ocean tsunami. Causes: subduction of Pacific Plate and other oceanic plates. Intense tectonic activity at convergent boundaries. Control seismic and volcanic monitoring networks. Tsunami early warning systems. Strict building codes in high-risk regions. Conclusion: the Pacific Ring of Fire is Earth's most active tectonic belt. While hazardous, it is also a source of resources and energy, showing the dual nature of geological processes. Shall I prepare Q15, causes of folding, and Q16, causes of faulting, next? Here are the next two Q&As, Q15 and Q16. Q15. What are the causes of folding? Definition: folding is the bending of rock strata due to compressional forces generated by tectonic movements. Facts: occurs at convergent plate boundaries. Responsible for formation of many mountain ranges. Body. Explanation: folding happens when pressure is exerted on sedimentary rock layers, making them bend instead of breaking. Causes of folding: 1 plate collision, converging plates push rock layers together. 2 horizontal compression, lateral pressure causes rocks to buckle. 3 plastic nature of rocks, soft and elastic rocks bend under stress. 4 tectonic stress and heat makes rocks ductile, allowing bending. 5 sediment accumulation, heavy loads compress underlying layers. Examples: the Himalayas, collision of Indian and Eurasian plates. The Alps, collision of African and Eurasian plates. Impact: mountain building. Earthquakes in folded regions. Creation of valleys and ridges. Causes: convergent boundaries, compressional tectonic forces. Control geological surveys to identify folding zones. Avoiding construction in unstable folded belts. Conclusion: folding is a key endogenetic process that creates major landforms, shaping Earth's surface and influencing human activities. Q16. What are the causes of faulting? Definition: faulting is the displacement or fracturing of rock strata due to tectonic forces exceeding the rock's strength. Facts: faults are classified into normal, reverse, strike-slip types. Associated with earthquakes and mountain building. Body. Explanation: faulting occurs when rocks are brittle and cannot withstand stress, leading to fractures and displacement. Causes of faulting: 1 tensional forces, rocks are pulled apart, normal fault. 2 compressional forces, rocks are pushed together, reverse fault. 3 shearing forces, rocks slide past each other, strike-slip fault. 4 sudden release of stress causes earthquakes. 5. Rigid nature of rocks makes them break instead of bend. Examples: San Andreas Fault, California. Great Rift Valley, East Africa. Narmada and Tapti Faults, India. Impact earthquakes. Rift valleys and block mountains. Disturbed drainage systems. Causes tensional, compressional, and shear stress at tectonic plate boundaries. Control earthquake-resistant construction. Fault line monitoring. Land use planning in seismic zones. Conclusion: faulting is a major geological process causing earthquakes and reshaping landscapes. It highlights the brittle behavior of Earth's crust under stress. Do you want me to continue with Q17, types of folds, and Q18, types of faults, next? Here are the next two Q&As, Q17 and Q18. Q17. What are the types of folds? Definition: folds are the bends in rock strata formed due to compressional tectonic forces. Facts found in sedimentary rocks indicate tectonic activity and crustal deformation. Body explanation: based on the intensity and shape, folds are classified as types of folds. 1. Anticline upward arch-like fold, limbs slope away. 2. Syncline downward trough-like fold, limbs slope towards each other. 3. Overturned fold, one limb tilted beyond vertical. 4. Recumbent fold, both limbs horizontal, lying parallel. 5. Isoclinal fold, limbs parallel and steep. 6. Monocline, one steep limb, one gentle limb. 7. Complex fold, irregular, highly deformed folds. Examples: anticline, syncline patterns in the Himalayas. Recumbent folds in the Alps. Impact mountain formation. Creation of ridges and valleys. Mineral deposits trapped in folds. Causes: horizontal compression, crustal stress, sediment load. Control: geological mapping. Planning settlements away from unstable folded regions. Conclusion: folds reveal the dynamic nature of the lithosphere and play a major role in shaping the Earth's mountain systems. Q18. What are the types of faults? Definition: faults are fractures in Earth's crust along which displacement of rocks occurs. Facts classified by the type of force acting: tensional, compressional, shearing. Fault zones are earthquake-prone. Body explanation: types of faults are: 1. Normal fault caused by tensional forces, 1 block slides down. 2. Reverse fault, thrust fault, caused by compressional forces, 1 block moves up. 3. Strike slip fault, lateral movement due to shearing forces. 4. Oblique fault, combination of vertical and horizontal movement. 5. Step fault, series of parallel faults causing step-like landforms. 6. Horst and Graben, uplifted, Horst, and down-thrown, Graben, blocks between parallel faults. Examples: San Andreas Fault, strike slip. Great Rift Valley, normal. Narmada Valley, Horst and Graben. Impact formation of rift valleys and block mountains. Earthquakes and surface rupture. Disturbance of river systems. Causes: tensional, compressional, and shear tectonic forces. Control: avoiding construction on active fault lines. Seismic monitoring and zoning. Earthquake-resistant infrastructure. Conclusion: faults demonstrate the brittle character of the crust and are vital in understanding earthquakes and landform development. Do you want me to continue with Q19, differences between folding and faulting, and Q20, significance of folding and faulting in landform development? Here are the next two Q&As, Q19 and Q20. Q19. Differentiate between folding and faulting. Definition: folding, bending of rock layers due to compressional forces. Faulting, breaking and displacement of rock layers due to tectonic forces. Facts: both are results of endogenetic forces. Folding shows ductile behavior, faulting shows brittle behavior. Body differences: aspect: folding, faulting, nature, bending of strata, breaking/displacement force, mainly compressional, tensional, compressional, shearing. Rock type: sedimentary rocks, ductile, all rock types, brittle. Landforms: formed fold, mountains, ridges, valleys, rift valleys, Block mountains earthquake association less direct highly earthquake-prone examples Himalayas, Alps San Andreas Fault, Narmada Rift examples folding Himalayas. Faulting Great Rift Valley. Impact folding builds mountains. Faulting causes earthquakes and rift structures. Causes folding, compression. Faulting, tension, compression, shear. Control land use planning in fault-prone areas. Seismic risk monitoring. Conclusion while folding uplifts and beautifies landscapes, faulting disrupts them violently, both remain fundamental to Earth's surface dynamics. Q20. What is the significance of folding and faulting in landform development? Definition: folding and faulting are tectonic processes that reshape the Earth's crust to form new landforms. Facts: they are key agents of orogeny, mountain building. Both operate under endogenetic forces. Body, significance, folding: 1 creates fold mountains, Himalayas, Rockies. 2 forms structural valleys and ridges. 3 traps minerals, coal and petroleum. 4 influences river courses. Faulting: 1 forms rift valleys, African Rift Valley, Narmada Valley. 2 produces block mountains, Vosges, Black Forest. 3 generates earthquakes shaping the terrain. 4 creates fault scarps and waterfalls. Examples: fold mountains Himalayas, Alps. Rift valleys Narmada, African Rift. Block mountains Sierra Nevada, Black Forest. Impact: enhances biodiversity by creating varied terrains. Provides natural resources. Causes natural hazards like earthquakes. Causes crustal compression, tension, and shearing. Control mapping tectonic zones. Avoiding urban development in active regions. Conclusion: folding and faulting are architects of Earth's landscape, shaping mountains, valleys, and basins while also posing hazards that demand human preparedness. Shall I move ahead with Q21, explain the types of earthquakes, and Q22, what are seismic waves and their types? Here are the next 2 Q&As, Q21 and Q22. Q21. Explain the types of earthquakes. Definition: an earthquake is the sudden shaking of the Earth's surface caused by the release of energy due to tectonic movements or other factors. Facts: measured using Richter scale and moment magnitude scale. Causes both constructive and destructive effects. Body, types of earthquakes. 1. Tectonic earthquakes caused by sudden movement of rocks along faults. Most common and destructive. Example: Nepal earthquake 2015. 2 volcanic earthquakes triggered by volcanic eruptions and movement of magma. Localized in volcanic zones. Example: Krakatoa eruption, 1883. 3 collapse earthquakes caused by the collapse of underground caves or mines. Small magnitude. Example: earthquakes in mining regions. 4 explosion earthquakes induced by nuclear tests or large explosions. Artificial in nature. Example: Nevada nuclear test site quakes. 5 reservoir-induced earthquakes caused by excessive water pressure in dams. Example: Koyna Dam earthquake, 1967. Examples: tectonic Nepal, 2015. Volcanic Krakatoa, 1883. Reservoir Koyna Dam, 1967. Impact: destruction of property and lives. Landslides, tsunamis, fires. Reshaping of landscapes. Causes: tectonic movements, volcanic activity, human actions. Control: earthquake-resistant structures. Seismic zone mapping. Early warning systems. Conclusion: earthquakes of various origins highlight the dynamic nature of Earth and the need for preparedness against such natural disasters. Q22. What are seismic waves and their types? Definition: seismic waves are vibrations generated by an earthquake that travel through the Earth's layers. Facts recorded by seismographs. Help in studying Earth's interior. Body, types of seismic waves. 1. Body waves, travel inside Earth. P waves, Primary waves longitudinal, fastest, travel through solids, liquids, and gases. S waves, secondary waves transverse, slower, travel only through solids. 2 surface waves, travel on Earth's surface. Love waves, cause horizontal shearing, highly destructive. Rayleigh waves, cause rolling motion, similar to ocean waves. Examples: P waves used in locating epicenters. Love and Rayleigh waves cause maximum building damage. Impact responsible for ground shaking and destruction. Provide clues about Earth's internal structure. Causes release of energy during fault movement or volcanic activity. Control designing quake-resistant buildings. Monitoring seismic activity. Conclusion: seismic waves not only cause destruction but also serve as natural probes to study Earth's structure and tectonic processes. Shall I continue with Q23, explain Richter and Mercalli scales, and Q24, what are aftershocks and foreshocks? Here are the next 2 Q&As, Q23 and Q24. Q23. Explain Richter and Mercalli scales. Definition: Richter scale, a logarithmic scale that measures the magnitude, energy released, of earthquakes. Mercalli scale, a qualitative scale that measures the intensity, damage caused, of earthquakes. Facts: Richter scale was developed by Charles F. Richter in 1935. Mercalli scale was developed by Giuseppe Mercalli in 1902. Body, difference between scales: 1. Richter scale measures magnitude. Ranges from 0 to 10. Instrument-based, seismograph. Example: 2011 Japan earthquake measured 9.0. 2. Mercalli scale measures intensity. Ranges from I to 12, Roman numerals. Based on human perception and structural damage. Example: 2001 Bujay earthquake intensity reached X. Examples: Japan 2011 Richter 9.0, Mercalli 11. Nepal 2015 Richter 7.8, Mercalli 9. Impact: Richter helps scientists compare quakes scientifically. Mercalli helps in assessing damage and planning relief. Causes sudden release of tectonic stress. Control seismic resistant construction. Public awareness of damage patterns. Conclusion: both Richter and Mercalli scales complement each other, one measuring energy and the other assessing destruction. Q24. What are aftershocks and foreshocks? Definition: foreshocks, small tremors that occur before a major earthquake. Aftershocks, smaller quakes that follow the main shock. Facts: both are part of earthquake sequences. Aftershocks can continue for weeks or months. Body, detailed explanation: 1. Foreshocks precede the main earthquake. Not always easy to identify. Example: foreshocks occurred before the 2011 Tohoku earthquake in Japan. 2. Aftershocks occur after the main earthquake. Gradually decrease in frequency and strength. Example: Nepal earthquake 2015 was followed by hundreds of aftershocks. Examples: Tohoku, Japan, 2011 strong foreshocks recorded. Nepal, 2015 series of aftershocks up to 6.7 magnitude. Impact: foreshocks may serve as warning signs. Aftershocks increase destruction and delay rescue. Causes: adjustment of rocks along faults. Control strengthening buildings to resist repeated shocks. Quick response teams to handle post-quake situations. Conclusion: foreshocks and aftershocks reveal the continuing adjustments within Earth's crust, demanding readiness before and after major earthquakes. Do you want me to move on to volcanic-related questions? Q25 and Q26, types of volcanoes, distribution of volcanoes, next. Here are the next 2 Q&As, Q25 and Q26. Q25. Describe the types of volcanoes. Definition: a volcano is an opening in the Earth's crust through which magma, gases, and ash escape. Facts: classified on the basis of activity and shape. Found mostly in plate boundary zones. Body, types of volcanoes. 1. On the basis of activity: active volcanoes erupt frequently, e.g., Mount Etna, Italy. Dormant volcanoes, quiet for long periods but may erupt again, e.g., Mount Vesuvius, Italy. Extinct volcanoes, no eruption in recorded history, unlikely to erupt, e.g., Kilimanjaro, Tanzania. 2. On the basis of shape-shield volcanoes, broad, gentle slopes, fluid lava, e.g., Mauna Loa, Hawaii. Composite or stratovolcanoes, cone-shaped, alternating layers of lava and ash, e.g., Mount Fuji, Japan. Cinder cone volcanoes, small, steep-sided, explosive eruptions, e.g., Paricutin, Mexico. Calderas, large depressions formed after violent eruptions, e.g., Yellowstone, USA. Examples: Mount Stromboli, Italy, active. Mount Fuji, Japan, dormant. Kilimanjaro, Tanzania, extinct. Impact: fertile soil formation. Hazards like lava flow, ash, and pyroclastic materials. Causes magma pressure buildup in weak crust zones. Control: monitoring volcanic activity with satellites and sensors. Hazard mapping and evacuation plans. Conclusion: volcanoes are both destructive and beneficial, shaping landforms and ecosystems while posing dangers to humans. Q26. Explain the distribution of volcanoes in the world. Definition: volcano distribution refers to the geographical pattern of volcanic activity on Earth. Facts: about 80% of volcanoes are located along plate boundaries. Pacific Ring of Fire is the most active volcanic belt. Body, global distribution, 1. Circum-Pacific Belt, Ring of Fire, accounts for nearly 2/3 of world's active volcanoes. Countries: Japan, Philippines, Indonesia, Chile, Mexico. 2. Mid-Atlantic Belt along Mid-Atlantic Ridge. Example: Iceland volcanoes. 3. Mediterranean Belt extends through southern Europe to Asia Minor. Examples: Mount Vesuvius, Mount Etna. 4. Other areas: African Rift Valley, e.g., Mount Kilimanjaro. Hawaiian Islands, intraplate hotspots. Examples: Krakatoa, Indonesia. Mauna Loa, Hawaii. Mount Etna, Italy. Impact: creation of new land, Hawaiian Islands. Major disasters causing loss of life and property. Causes: plate subduction, divergence, and hotspots. Control: international volcanic monitoring networks. Evacuation strategies in high-risk zones. Conclusion: volcanoes are unevenly distributed, concentrated mainly along tectonic plate boundaries, showing the dynamic nature of Earth's lithosphere. Would you like me to continue with Q27 and Q28, volcanic landforms intrusive and extrusive, next? Here are the next two Q&As, Q27 and Q28. Q27. Describe the intrusive volcanic landforms. Definition: intrusive volcanic landforms are created when magma cools and solidifies below the Earth's surface. Facts: magma does not reach the surface. Forms: crystalline igneous rocks. Body: types of intrusive landforms. 1. Batholiths: large, dome-shaped masses of igneous rocks. Example: Sierra Nevada, USA. 2. Laccoliths: dome-shaped intrusions that uplift overlying strata. Example: Henry Mountains, USA. 3. Sills: horizontal sheets of igneous rock between layers. Example: Great Hwyn Sill, UK. 4. Dikes: vertical wall-like intrusions cutting across layers. Example: Deccan Dikes, India. 5. Faccoliths: lens-shaped intrusions in folded rocks. Examples: Deccan Trap Dikes, India. Henry Mountains, USA. Impact: source of building materials. Influence: landscape features after erosion. Causes: magma movement into weak crustal zones. Control: not preventable, but geological surveys help in identifying mineral-rich zones. Conclusion: intrusive landforms showcase the hidden activity of volcanoes, shaping landscapes over geological timescales. Q28. Describe the extrusive volcanic landforms. Definition: extrusive volcanic landforms are created when magma erupts onto the Earth's surface and solidifies. Facts: lava cools rapidly. Forms fine-grained igneous rocks. Body, types of extrusive landforms. 1. Volcanic cones: cinder cones, shield volcanoes, composite volcanoes, e.g., Mount Fuji, Japan. 2. Calderas: large depressions formed after violent eruptions, e.g., Crater Lake, USA. 3. Lava plateaus: extensive flat surfaces from successive lava flows, e.g., Deccan Plateau, India. 4. Volcanic domes formed by viscous lava piling up, e.g., Mount Pelee, Caribbean. 5. Fissure eruptions: lava escapes through cracks, covering vast areas, e.g., Columbia Plateau, USA. Examples: Deccan Trap, India. Mauna Loa, Hawaii. Mount Vesuvius, Italy. Impact creates fertile soils. Destructive eruptions impact life and property. Causes: plate movements and magma pressure release. Control: early warning systems and volcanic hazard mapping. Conclusion: extrusive landforms demonstrate the surface expression of volcanism, reshaping landscapes and supporting human life despite hazards. Do you want me to continue with Q29 and Q30, earthquake, definition, types and causes, next? Here are the next two Q&As, Q29 and Q30. Q29. Define earthquake and explain its types. Definition: an earthquake is the sudden shaking or trembling of the Earth's crust caused by the release of energy due to tectonic stresses. Facts: measured on the Richter scale, magnitude, and Mercalli scale, intensity. Caused by faulting, volcanic activity, or isostatic adjustments. Body, types of earthquakes. 1. Tectonic earthquakes due to movement along faults. Example, Nepal earthquake, 2015. 2. Volcanic earthquakes associated with volcanic eruptions. Example, Mount Krakatoa eruption, 1883. 3. Collapse earthquakes caused by collapse of underground caves/mines. Example, mining areas of Pennsylvania, USA. 4. Explosion earthquakes result of nuclear tests/explosions. Example, Nevada test site, USA. Examples: Bajaj earthquake, 2001, India. San Francisco earthquake, 1906, USA. Impact: loss of life and property. Landslides, tsunamis, fires. Causes: plate tectonics, volcanic activity, man-made explosions. Control: earthquake-resistant buildings. Seismic monitoring and early warning systems. Conclusion: earthquakes are powerful natural hazards whose understanding helps in reducing their disastrous impacts. Q30. Explain the causes of earthquakes. Definition: causes of earthquakes refer to the geological and tectonic forces responsible for sudden ground shaking. Facts: most earthquakes occur along fault lines. 90% are associated with plate boundaries. Body, causes of earthquakes. 1. Plate tectonics: collision, subduction, or sliding of plates creates stress. Example, Himalayan region, India. 2. Faulting and fractures: sudden slip along fault lines releases energy. Example, San Andreas Fault, USA. 3. Volcanic activity: rising magma triggers tremors. Example, Iceland volcanic zone. 4. Isostatic adjustments: crustal balancing after glacier melting or erosion. 5. Human activities: nuclear tests, dam-induced seismicity, reservoir triggered. Example, Koyna Dam earthquake, 1967, India. Examples: Gujarat earthquake, 2001. Sichuan earthquake, 2008, China. Impact: ground rupture, infrastructure damage, tsunamis. Control: seismographic networks. Hazard zoning and earthquake-resistant designs. Conclusion: understanding causes of earthquakes is crucial for preparedness and minimizing risks to human society. Shall I continue with Q31 and Q32, earthquake waves and focus/epicenter concepts? Here are the next two Q&As, Q31 and Q32. Q31. What are earthquake waves? Explain their types. Definition: earthquake waves are vibrations that travel through the earth after the sudden release of energy at the focus of an earthquake. Facts recorded by seismographs. Travel at different speeds through solids, liquids, and gases. Body, types of earthquake waves. 1. Primary waves, P waves, longitudinal, fastest, travel through solids, liquids, gases. Push-pull motion, compressional. 2. Secondary waves, S waves, transverse, slower than P waves, travel only through solids. Up-down and side-to-side motion. 3. Surface waves, L waves, travel along the Earth's surface. Cause maximum destruction. 2 types, Love waves and Rayleigh waves. Examples: P and S waves recorded during Nepal earthquake, 2015. Surface waves caused massive damage in Gujarat earthquake, 2001. Impact P waves arrive first, giving scope for early warning. S and surface waves cause building collapses and loss of life. Causes generated by sudden release of stress in lithosphere. Control: seismographic monitoring. Early warning based on arrival of P waves. Conclusion: earthquake waves help scientists study Earth's interior and prepare for disasters. Q32. Differentiate between focus and epicenter of an earthquake. Definition: focus, hypocenter point inside the Earth where earthquake originates. Epicenter, point on the Earth's surface directly above the focus. Facts: focus can be shallow, intermediate, or deep. Epicenter is the location reported in news. Body, differences, aspect: focus, hypocenter, epicenter location inside the Earth, point of origin on surface, directly above focus. Depth varies from shallow to deep, always on the surface. Energy release: strongest point where stress is released, place where shaking is felt. Detection measured by seismographs marked on maps/reports. Example: Nepal EQ focus 15 km deep, Kathmandu epicenter. Examples: Nepal earthquake, 2015 focus 15 km deep, epicenter near Gorkha. Bajaj earthquake, 2001 focus 25 km deep, epicenter in Bajaj, Gujarat. Impact areas near epicenter face maximum destruction. Deeper focus spreads shock over larger area. Causes tectonic stress accumulation in crust. Control: hazard mapping around epicentral zones. Preparedness programs in seismic hotspots. Conclusion: both focus and epicenter are vital in understanding earthquakes and planning disaster management. Do you want me to move next to Q33 and Q34, measuring earthquakes and Richter scale? Here are the next two Q&As, Q33 and Q34. Q33. How are earthquakes measured? Definition: measuring an earthquake means recording its magnitude, energy released, and intensity, effects on people and structures. Facts: instruments, seismograph, seismometer. Scales: Richter scale, moment magnitude scale, Mercalli intensity scale. Body, methods of measurement. 1. Magnitude: energy released at the focus. Richter scale, 0-10. Moment magnitude scale, modern, more accurate. 2. Intensity: damage and effects felt on the surface. Mercalli scale, I-12. Examples: Nepal earthquake, 2015 magnitude 7.8, intensity 9. Bajaj earthquake, 2001 magnitude 7.7, severe damage in Gujarat. Impact magnitude helps compare global earthquakes. Intensity helps in relief and reconstruction planning. Causes: tectonic release of energy at the fault line. Control: use of advanced seismographs. Global earthquake monitoring networks. Conclusion: measuring earthquakes is essential for early warning, scientific understanding, and minimizing disaster losses. Q34. What is the Richter scale? How does it work? Definition: the Richter scale is a logarithmic scale developed by Charles F. Richter in 1935 to measure earthquake magnitude. Facts: ranges from 0 to 10, theoretically no upper limit. Each whole number increase equals 10 times stronger waves and 32 times more energy. Body, working of Richter scale. 1. Records amplitude of seismic waves on a seismograph. 2. Calculates energy released using a logarithmic formula. 3. Magnitude assigned to earthquake, e.g., 5.5, 7.2. Examples: 2001 Bajay earthquake, 7.7 on Richter scale. 2011 Japan earthquake, 9.1 on Richter scale. Impact provides standard comparison for earthquakes worldwide. Used in disaster planning and engineering. Causes sudden energy release at tectonic fault lines. Control worldwide seismographic networks use Richter scale. Helps prepare earthquake-resistant structures in high-magnitude zones. Conclusion: the Richter scale remains a vital tool in earthquake science, helping assess risks and safeguard human lives.